Since the 5th century, scientists have come a long way in discovering what an atom is and what is it made of. From Democritus' first atomic theory, which stated that all matter is made up of tiny indivisible particles, he called atomos, to Rutherford's theory in 1911, saying that the atom is composed of neutrons and protons held together in what we call a nucleus, and surrounded by negatively charged electrons which are attracted to it. He came to conclude that the electrons must move to remain apart from the nucleus, so that the energy of the electrons' movement balance the energy of attraction, otherwise they get closer and closer together till they collide, and at this point there won't be no atoms, no matter, and no universe. In 1913, a Danish physicist called Niels Bohr presented his atomic model in order to explain the stability of the atom, suggesting that electrons move in fixed circular paths, or orbits, similar to how planets spin around the sun. In fact, he was more concerned with the hydrogen atom. He wanted to explain the behavior of the electron in the hydrogen atom and how it is even responsible for the light emitted from the hydrogen atom when it gains enough energy. When hydrogen atoms get heated, for example, they emit light, often observed as a pinkish color. Bohr proposed that this emission is due to the electron transitioning between different energy levels within the atom. These orbits are referred to as energy levels or shells, each designated by an integral number known as the principal quantum number n. The larger its value, the further from nucleus the orbit is. These orbits are quantized, meaning that electrons can only exist at specific distances from the nucleus and can't be somewhere in between these orbits. The distance of each orbit is referred to as the radius of the orbit, which can be calculated using this equation. Typically, the electron would move in a straight line, but the attraction of the positive proton in the nucleus bends its path so that it moves with a constant velocity in a perfect circle around the nucleus. This circular movement creates a centrifugal force, which gives the electron the tendency to fly away from the nucleus. The electrostatic or the attraction force between the positive proton and the negative electron is described by Coulomb's law, where K is the Coulomb's constant, Q1 and Q2 are the proton and electrons' charges in opposite signs, and Z is the number of protons. The centrifugal force relation is given by Fc, where me is the mass of the electron and v its velocity. In Bohr's model, for a stable orbit, these two forces must be equal. Using this equation, Bohr was able to derive the radius of the orbit expression, in addition to the velocity of the electron in a given orbit, among other expressions. Under normal conditions, the single electron in a hydrogen atom occupies the lowest energy level, which is called the ground state. It is the closest orbit to the nucleus. The second and all higher energy levels or orbits are called excited states. When electrical current or heat is supplied to the hydrogen atom, the electron absorbs the appropriate amount of energy needed to jump from the ground state to a higher energy level. Since energy levels are quantized, the energy absorbed or emitted is equal to the difference of energy between the two levels that the electron occupied. To find the amount of energy absorbed when the electron jumps from the first orbit to the third orbit, we calculate the difference in energy between these levels. Each orbit has its own energy. Bohr was able to determine these energies using this equation, where E0 represents the energy of the electron in the ground state, with a value of -13.6 electron volt. Now we calculate the absorbed energy between the two energy levels. So, the electron absorbs approximately 12.09 electron volt of energy when it jumps from the first orbit to the third orbit in a hydrogen atom. Once the electron is in a higher energy level, it will fall back to the first energy level by losing the same amount of energy needed for the uphill transition, but in the negative sign, indicating that energy is released. We can then say that the energy levels of the electron are quantized. When an electron in a hydrogen atom transitions from a higher energy level to the second orbit, the energy released can be emitted as a photon of light of a red color. If we keep sending energy to the hydrogen atom, the electron can pass through several orbits or transitions. The visible transitions observed when electrons fall to the second orbit produce distinct colors within the visible spectrum. The pinkish color seen before is composed of several electron transitions or photon energies and wavelengths. The emitted light can be separated into distinct colors using a prism. Each atom has its own unique emission spectrum, which acts like a fingerprint for identifying the atom. This means different atoms emit different radiations when excited. For example, the transition from the third to the second energy level results in a change in energy of minus 1.89 electron volt, calculated as the difference between the energy levels. We can calculate the wavelength of the photon emitted using the relation between energy and wavelength, where h is the Planck's constant, in the unit of electron volts times seconds, and c is the speed of light. So the wavelength corresponding to an energy difference of minus 1.89 electron volt is approximately 656 nanometers, which falls within the red part of the visible spectrum. However, not all emitted radiation is visible to the human eye. For example, if an electron falls back to the first orbit, it emits a photon with a wavelength in the ultraviolet region. Conversely, if the electron falls back to the third orbit, the emitted photon may fall in the infrared region. The hydrogen spectral lines are classified into several series based on the final energy level of the electron after it transitions. The most notable are these series. Bohr's model was significant for our understanding of atomic structure. However, it doesn't fully explain the complexities of how atoms behave. The concept of fixed orbits implies a level of certainty regarding an electron's position and velocity, which aligns with classical physics. However, as we explore more, we recognize that this classical perspective is insufficient. Soon after Bohr's model was presented, a French physicist named Louis de Broglie introduced the idea of the wave-particle duality, suggesting that particles such as electrons have properties both of a particle and of a wave, and cannot be viewed only as simple points orbiting the nucleus in circular paths. According to Louis de Broglie, every particle can exhibit wave-like properties. The wavelength associated with a particle is described by the de Broglie wavelength equation, where lambda represents the de Broglie wavelength. This wavelength is inversely related to the particle's momentum, which is defined as the product of its mass and velocity. The de Broglie wave-particle duality hypothesis was confirmed in the late 1920s through experiments conducted by Clinton Davison and Lester Germer. They demonstrated this duality using electron diffraction, which was analogous to the famous double-slit experiment originally conducted by Thomas Young with light. In his experiment, Thomas Young shone light through two closely spaced slits onto a screen. The resulting pattern displayed alternating bright and dark fringes, indicating interference, an essential characteristic of wave behavior. This interference pattern suggests that light behaves like a wave, exhibiting constructive and destructive interference. However, this result is tied to the concept of measurement. When both slits are open, and no measurement is made to determine which slit a photon passes through, both constructive and destructive interference appear. Conversely, if a measurement is made to determine the path of the photon, the interference pattern disappears. Instead, light behaves like classical particles, impacting the screen into distinct bands, corresponding to the two slits. This indicates that light can exhibit both wave-like and particle-like behavior. In the context of quantum mechanics, the experiment was revisited to illustrate the dual nature of particles like electrons. Davison and Germer replaced the light source with an electron gun, shooting electrons through the two slits. Electrons displayed the same wave-particle duality as light. When electrons were fired individually, they created an interference pattern, suggesting that each electron behaves like a wave. However, when the path of the electrons was observed, they behaved like particles. This remarkable demonstration validated de Broglie's hypothesis and contributed to his recognition with the Nobel Prize. The experiment demonstrated that particles can exhibit both wave-like and particle-like properties depending on the circumstances. This result highlights the fundamental principles of quantum mechanics, including superposition and the influence of observation on quantum systems. Following de Broglie, Werner Heisenberg further challenged the classical ideas with his uncertainty principle. This principle states that the more precisely we know an electron's position, the less precisely we can know its momentum, and vice versa. This means that we cannot determine an electron's exact path and momentum in the way Bohr proposed. Instead, we must think in terms of probabilities. The idea of probability came from the observation that each time we would locate an electron, it would most likely be in a different position than before. However, if we take enough measurements, a pattern would develop. This brings us to the concept of electron clouds, where we consider electrons as areas of a probability density. Three-dimensional shapes that represent the probability distribution of an electron's position indicating the likelihood of finding a particle in a specific location. A cloud is generally called an orbital, which is a different concept from Bohr's orbit. An orbital is visualized as an electron cloud, as if the electron was spread out in a volume of space like a cloud. There are 4 different types of orbitals: the s, p, d, and f orbitals. Each type of orbital has a specific shape and can hold a designated maximum number of electrons. The s orbitals have a spherical shape, centered around the nucleus. The electron density is uniform in all directions and can hold a maximum number of 2 electrons. The p orbitals are shaped like dumbbells. There are 3 p orbitals oriented along different axes. Each p orbital consists of 2 lobes, with each lobe capable of holding 1 electron. Therefore, a single p orbital can hold up to 2 electrons, and collectively, the 3 p orbitals can accommodate a maximum of 6 electrons. D orbitals have more complex shapes, often resembling clovers or donuts. There are 5 distinct d orbitals, each with unique orientation, and they can hold a maximum of 10 electrons with 2 electrons in each orbital. F orbitals can have shapes resembling flowers with multiple lobes. There are 7 orientations for F orbitals, allowing them to hold a maximum of 14 electrons. The orbit that Bohr described still holds significance in modern atomic theory, but it is now referred to as a shell. Just as Bohr's orbits can hold multiple electrons, a shell can encompass more than 1 cloud of electrons, or orbitals. The orbitals of the same type within each shell make up what is known as a subshell. The first shell consists of only one s orbital, or the s subshell. The second shell contains both the s subshell and 3 p orbitals, or the p subshell, which are larger than those in the first shell. The third shell holds the blue s subshell, the p subshell, and 5 more d orbitals, or the d subshell. The fourth shell encompasses all 4 types of orbitals: the s, p, d, and f subshell. We can observe that each successive shell is larger and includes an additional type of orbital, illustrating the increasing complexity of electron arrangements as you move further from the nucleus. Each electron in an atom is described by a set of 4 numbers, known as quantum numbers. These numbers provide essential information about the electron state. The first number, n, is the principal quantum number, which indicates the energy level or the shell number as well as the size of the orbitals where the electron belongs. The second number is the angular quantum number, which describes the shape of the subshell or orbital to which the electron belongs. It can take on values from 0 to n-1. For example, if n equals 1, L is 0, indication of the s subshell. If n is 2, then L is 1 and the subshell type is p, and so forth. We have also the quantum number m sub L, which is the magnetic quantum number. This number specifies the orientation of orbitals in space, where a particular electron resides. M sub L can range from -L to L. For instance, if L equals 0, M sub L is then 0. It can have 1 value, meaning 1 orientation. If L is 1, M sub L can take 3 values, -1, 0, and 1. That means there's 3 orientations for p orbitals in the p subshell, and so on. And finally, we have the spin quantum number m sub s, which indicates the direction of the electron spin. An electron that behaves as both wave and a particle is also a charged particle that spins on its axis. It may spin either in the clockwise direction with a value of +1/2, or in the anti-clockwise direction with a spin value of -1/2. We can know the direction of spinning by observing the magnetic field because the spinning of a charged particle creates a magnetic field. In an orbital, there can be 1 or 2 electrons, with one spinning up and the other spinning down, but they cannot have the same spin direction. Together, these quantum numbers provide a complete description of an electron state and its arrangement in atoms. According to the Pauli exclusion principle, no 2 electrons in an atom can have the same set of quantum numbers. Energy is a fundamental concept in atomic structure. influencing the behavior and arrangement of electrons within an atom. In the context of quantum mechanics, the energy of an electron is primarily determined by its distance from the nucleus and the type of orbital it occupies. As successive shells have higher size, they also have higher energies. As we move to higher principal quantum numbers, the energy of shells increases. This means that electrons in higher shells are generally further from the nucleus and have higher potential energy. Additionally, within a given shell, the energy of subshells increases in the SPDF order. When we talk about energy of subshells between shells, the 2s subshell, for example, has higher energy than the 1s subshell. The 2p subshell, on the other hand, has a higher energy than both the 1s and 2s subshells. Interestingly, the 3d subshell has a higher energy than the 3p subshell and all subshells from previous shells. However, if we look carefully, we can observe that the 3d subshell is positioned above the 4s subshell, indicating that it also has a higher energy than the 4s subshell. This is an important concept in understanding electron configuration and the filling order of orbitals, which will be discussed in the next video.